We want to graph h of x equals the cube root of x minus 4. And we're wanting to graph this without our calculators, and we want to use our knowledge of transformations. So we'll begin by identifying the parent function. So to identify the parent function, think of stripping this function, stripping all the numerical values away from this function. So in other words, we'd be ignoring this negative 4, or subtraction of 4, and what we're left with here would be our parent function. So our parent function is going to be y equals the cube root of x. And then the subtraction of 4, the minus 4, is going to cause a transformation. So we have a parent function and we have our transformation, and this minus 4, because the minus 4, you can see it's outside of the parent function, this means we're taking our y values and we're subtracting 4. So every y value is going to be 4 less than it was before, and that's going to graphically cause the function to shift down 4. So we've identified our parent and our transformation. So now we want to graph the parent function. So trying to graph the parent function without any of our notes or without our calculator. If you have a good idea of the basic shape, that's a great start. If you don't, then you kind of need to make a table in your head. So let's go ahead and start with 0 and some positive values, and then we'll also look at some negatives. So if we were going to input 0, and again we're looking at the parent function here, the cube root of 0 is going to be just 0. Inputting 1, the cube root of 1 is 1. Now the cube root of 2 is going to be some decimal, and that would require our calculator. So we'll go further. Cube root of 3, cube root of 4, 5, 6, and on. You'll notice all of those are going to be decimals until we get to 8. The cube root of 8 will give us 2. So we see that the right-hand side of the function is going to look something like this. But now we need to consider negative values as well. So it's important to remember that because we have an odd index, and remember that the index here, in this case a cube root, the index is a 3, because we do have an odd index, it's okay to have negative values inside this radical. So for instance, the cube root of negative 1, we know is going to be negative 1. So we have a point down here that we can plot, negative 1, negative 1. And then the cube root of negative 2 will be a decimal, same with the cube root of negative 3 and on, and we'll go all the way out to negative 8. So the cube root of negative 8 we know is negative 2. So we can see, oops, try that again, sorry. We can see that we have a piece of the graph here as well. And now we've graphed the entire parent function. It's sort of this elongated S-shaped graph. And now we're going to just take every single point and we will move them all down 4. So starting with my left-hand point here that was at negative 8, negative 2, I'm just going to count down 4, and then I'm going to plot my new point. And the point here, which was negative 1, shifts down. And I have my new point. And the one at the origin, 0, 0, shifts down 4. And I have my new point. So doing this with all of our 5 points that we graphed, we'll create our shifted function. And then connecting with a nice smooth curve, we see it's the same exact shape as the original parent function, but it's been shifted down 4. And then just go ahead and label that this would be h of x. Now let's go ahead and talk about domain and range while we're here. So the domain, we're talking about the domain for my finished product here, my red function, which is h of x. Remembering that domain's asking you for the x values. What kind of values are we allowed to input into the function? So you can figure the domain from the original function, the cube root of x minus 4, in that you're allowed to put negatives, positives, and 0 into a cube root. So we should see that our domain is all real numbers. And our graph confirms this because you can see the graph goes left forever and right forever. Now your range, remember, is lowest to highest. Probably easiest to look at your graph here to see that we have this arrow here on the left-hand side. Not only is it going left forever, but it's also going to be inching its way down forever. And also on the right side, it's going right forever, but also inching its way up forever. So therefore the range would also be all real numbers. So the next function we want to graph is g of x equals x squared plus 3. So once again, trying to identify the parent function, think of taking away all the numerical values. So in other words, this positive 3 here, we're going to ignore that for right now, and what's left will be our parent function. That would give us y is equal to x squared. Notice I don't just write x squared here. It's important that you do write y equals x squared so that you're giving me a function and not just an expression. Now this plus 3 impacts our graph. We have a transformation. In this case, it's going to be a shift. Basically, you're adding 3 to all of the y values, which means this is going to be a vertical shift up 3. So we'll begin by graphing the parent function. Once again, trying not to rely on technology, not wanting to use our graphing calculators or notes. So trying to generate the graph of y equals x squared. So you can kind of make a mental table. Hopefully you automatically realize that the basic shape is a parabola. It's a U-shaped graph that's going to be opening up. But let's go ahead and make a table. So once again, thinking about whether we can have negative values and positive values. Can we put a negative value in and square it? And the answer should be yes. And a positive, absolutely. Usually people are most comfortable with the positive. So if we plug in 0, we know that the output is going to be 0. Substituting positive 1 squared is 1. We know that 2 squared is 4. And 3 squared is 9. But of course we can also input negative values. So negative 1 squared will give us positive 1. Sorry about that, having trouble getting my points plotted here with this program. Try again. Negative 2 squared will give us 4, and negative 3 squared will give us 9. So we have our basic shape for the parent function, which is this nice parabola that opens up. And then we'll go ahead and take all of our points, and we'll shift them up 3. So starting with the vertex, which was at 0, 0, if you shift up, now we'll have a new vertex here at 0, 3, and then every individual point shifts up as well, thereby generating our new graph, which has been shifted. See if we can get all the points here. Here we go. So we've shifted all of our points, and we now have our new shifted graph, same exact shape as the parent function. Same shape, just shifted up 3. Look at domain and range quickly. So once again, domain. It's important that you can compute the domain not just from looking at the graph, but looking at the actual original function. So domain asking, what is x allowed to be? What kind of values can we substitute here in for x? And since we're just squaring the numbers, we can substitute any sorts of values that we want, meaning all real numbers would be the domain. And the graph supports this. My red graph, you can see it goes left and right forever. And then the range, graphically you can see that my lowest point on the graph here, that y value is negative 3, and then the arrows at the top indicate that it continues forever to positive infinity. So my range is going to be from 3 to infinity. And then we want to use a bracket on 3 because that point is included on this graph. So range is from 3 to infinity. Now we want to graph f of x equals the square root of x minus 2. So identifying our parent function, if we ignore the minus 2, then we're left with y is equal to the square root of x for my parent function. Then looking at the minus 2, that tells us that our y values are all going to be 2 smaller than before, meaning that the whole graph is going to shift down 2. So our transformation would be a vertical shift down 2. So now let's go ahead and graph our parent function. So y equals the square root of x. What kind of numbers are we allowed to substitute here into the parent function for x? Remember, because the index is even, we cannot take the square root of a negative number if we're looking at just the real numbers. So we're not going to have any negative values. But we could certainly do 0. The square root of 0 is just 0. Square root of 1 will give us 1. Square root of 2 would be a decimal. Same with the square root of 3. But the square root of 4, we should know, square root of 4 will be 2. We could keep going here if you have room. Square root of 5, square root of 6, square root of 7. Again, all of those would be decimals all the way until we get to 9. The square root of 9 will be 3. So we've generated our parent function by kind of making a mental table. And now we'll go ahead and shift this function. All 4 of the points that I've graphed are going to be shifted down too. So my initial point here, which was at 0, 0, it's going to shift down 2 and be at 0, negative 2. And then you go ahead and just shift all the resulting points down 2. And the shape of my new function is the same as the shape of the parent. It's just been shifted. So always mark your final answer. My final answer there is f of x. Now let's look at domain and range again. So I'll put these over here. Domain and range. Remembering that we want to be able to figure out the domain from the original function, not just from looking at my graph. Okay? If you can figure out the domain for the original function, that's actually a way of checking your graph. Because if you made a mistake on your graph, then you don't want to use your graph to figure out the domain. Obviously, you'd be missing 2 parts of a problem. So let's figure out the domain from the original function. So remember, we have restrictions for the types of numbers that you can have inside of a square root. So inside this square root right now is just plain x, and we know that we can't have negatives inside of a square root. Now, can we have 0? Absolutely, because remember, the square root of 0 is just 0. So how do we write that mathematically? We write that x, which is the quantity inside that square root, must be greater than or equal to 0. Which, written in interval notation, would be from 0 to infinity with a bracket on the 0, because we would include it. And then if you take a look at this red graph that we graphed, f of x, our graph supports the domain, that it starts at 0 and then travels to the right to positive infinity. Now you can use your graph for the range, remember, which is lowest to highest. So the lowest point on this graph, the y value is negative 2. The highest point on the graph would be infinity, remembering that the arrow here to the right-hand side of the graph also indicates that it's going to be moving up. And then we would want to include negative 2 because it is a point on the graph. So that would be a bracket. Negative 2 to infinity would be our range.